at nuclear reactions, we're going to do two things, or three things really, two of which are almost the same. We're going to distinguish between fission and fusion. We're going to explain how a chain reaction is utilized, and we're going to compare fission and fusion reactors. Okay, the difference between them. With the definition of a nuclear reaction. A nuclear reaction is any process that involves a change in the nucleus of an atom. In the nucleus of an atom. So, we've been talking about electrons moving through circuits. We've been talking about, static charge, where if you rub a balloon on your hair, part of the electrons jump from your hair to the balloon. So, it's pretty easy for electrons to move, right? And then you get a little shock maybe, or something happens, you're a little charged particle, you get shocked when you touch something. Now, big difference here. The minute you alter a nucleus, much more energy is released. So nuclear reactions are much, much more difficult to harness and to create than some sort of, change of electrons, which is easy. If there's an imbalance in charge, the electron moves. Nuclear reactions, what is the nucleus held together by? The nucleus, what is it held together by again?
Force.
What force?
Strong nuclear.
The strong force. Now, if the strong force is holding it together, and the strong force is one of our stronger forces of the four fundamental forces, it takes a lot of energy to split apart a nucleus and a lot of energy to combine two nuclei into one. So fission and fusion involve a lot of energy. Fission and fusion are things that were used to make bombs. So the first nuclear bomb was a fission bomb. The first hydrogen bomb was a fusion bomb, actually. And in those cases, what the goal was to have an uncontrolled nuclear reaction that was catastrophic and killed a lot of people. Now, what we want today are controlled reactions, and that's where you get nuclear reactors. Has anyone heard of Chernobyl? Does anyone want to explain what happened or what Chernobyl? Chernobyl? I don't know. Chernobyl. I don't know. It's in Russia somewhere, right? Forget about it.
Didn't like a nuclear reactor have a meltdown?
Yeah, there was a nuclear meltdown. And as a result, the neighboring area has been poisoned with radiation. The people that worked there, a lot of them died. A lot of them that didn't die still got poisoned with radiation. The entire area cannot grow crops, so crops were not able to be grown. Same thing happened when the nuclear bomb was dropped, when the hydrogen bomb was dropped. When that kind of stuff happens, we don't consider the long-term effects of radiation. Because when this nuclear reaction occurs, so much radiation is given off. It's not always that people are sure, people in the blast radius, honestly, they're just melted. You are disintegrated. You vaporize. The heat, you wouldn't even feel it.
Oh, okay.
The heat, the thermal energy that comes off of a nuclear bomb is so great that anything in the blast radius, anything especially organic, meaning people or plants or anything life, dies instantly. It'll shrivel up, it'll literally vaporize off. There might be remains of bones left behind at the most. But not only that is a big thing, but for years to come after, people are constantly showing up with diseases, with mutations, with issues with the food that they eat. If they eat certain food from that area, they can get radiation poisoning from the food itself. So years down the line, these bombs have a long-term effect. So nowadays, it's not really let's use a bomb, because hopefully we have a little more peace in the world where we don't need major bombs. Imagine if World War III existed though. It wouldn't be a militia war anymore. It wouldn't be Marines. It wouldn't be Navy. Marines and Navy they're useful now, obviously, because they keep safe certain areas of the world. They help certain things. But World War III would be a nuclear war. So many countries have nuclear warfare now that it's a little bit scary to think about. When they talk about nuclear winters, a nuclear winter would be if enough nuclear bombs went off and the Earth's atmosphere got screwed up and all the plant life started to die. A nuclear winter would be something like, you don't have crops in the wintertime. Everything would turn into a constant phase of winter where nothing is growing. You have desolate areas. So that's a big fear in the world, obviously, especially countries that may be countries that are unstable countries with unstable governments and dictators that have their hands on nuclear devices. Now, we are lucky in the U.S. to have such amazing technology that the U.S. would really never be hit by a nuclear bomb from another country. If a nuclear bomb ever went off in the U.S., it would have to be something that was built in the U.S. If a nuclear bomb is, launched toward the U.S., what do we have in place?
He has like a space, I think it's called Star Wars system.
I don't know what it's called, but
Submarine posed that we never actually did it. And plus, Russian Akula class submarines can hit us because they have cruise missile nukes, so they can go to our source and hit us.
so subs good, you're saying?
Yeah, they're submarine. They don't fly in the atmosphere as high as like regular. They like low flying and stuff like this.
No, but I'm pretty sure we have missiles set up on the Virgin Islands in case.
We, as a country, are supposed to have, and obviously nobody knows because we're not, have clearance and stuff like that, and B, none of us are in the military here, okay? But the theory and the idea is that the country has enough technology to be able to react automatically as like a system feedback. So if there was an incoming missile, it launches something into the air to cause that missile to go off somewhere in the atmosphere that wouldn't hurt people. Now, I don't know exactly what Nick was referring to with low traveling missiles, but I'm sure that what he's saying is right also, okay? So the idea of nuclear reactions, that it's extremely, extremely great amounts of energy. Okay, that's what we need to think about and keep that in the back of your mind. So let's take a look here. What's happening here is this nitrogen atom, okay, is being bombarded by an alpha particle. An alpha particle is just simply the helium nucleus. It's 2 protons and 2 neutrons, giving it a mass of 4. So it's an alpha particle. So an alpha particle bombards the nitrogen nucleus, and as a result, they form intermediate nucleus or nuclei. And those intermediate nuclei are fluorine and oxygen. And a byproduct, okay, a byproduct of this is this hydrogen atom. Okay, so this is an example of a nuclear reaction. Again, because the nucleus changes. That's how you know it's a nuclear reaction. When it's a simple chemical reaction, okay, you get molecules that combine from results of 2 other molecules, but you don't have a change in the actual atom. These are completely different atoms from what we started with.
Why doesn't it say why does it become oxygen and hydrogen also?
Let me think for a second. So, it becomes fluorine, and I'm thinking about why, now I know why. It becomes fluorine, but this is an unstable isotope of fluorine. So, the result of an alpha particle combining with nitrogen becomes an unstable fluorine particle. Where's fluorine on our periodic table? Anybody know what?
It's on
But its mass is 9, but its atomic number is 9, but I don't think its mass is 18. Its stable form, I think the mass might be 20. Can somebody check the mass of fluorine? The atomic number is definitely 9.
Yeah, 18.99.
So 919 is the stable form. So fluorine in its stable form has 9 protons and 10 neutrons. Remember I kept saying to you, if something wants to be stable, you want it to have more neutrons than protons. So the stable form of fluorine is this. This is the stable form. But we get this isotope that's unstable. That unstable isotope then undergoes, I think it's radioactive decay. Is it radioactive decay? It's decay, but I'm trying to think if it's radioactive or not, if hydrogen atoms come off. It undergoes some sort of decay process which breaks it into oxygen and hydrogen. Okay? 2 different gases.
Is it more unstable if it has less neutrons than it's supposed to have? Like if it has...
Absolutely.
Okay.
Fewer neutrons, the less stable it is, every time. More neutrons, more stable it is. Okay? You always want to have more neutrons than protons to increase stability. All right. Let's talk about fission to start. Fission. So fission is any nuclear reaction where a nucleus splits into 2 or more nuclei. 2 or more nuclei. Now, fission occurs when atoms are unstable. Okay? When atoms are unstable. When we have large atoms. And we're looking at atoms larger than 58 on the periodic table. 58 is your cutoff point. Atoms larger than 58 traditionally undergo fission, while atoms less than 58, we're going to see in a moment, undergo fusion more often than fission. Okay, 58 is not like, it's not like one or the other happens there, but that's a good cutoff point generally.
And the thing with
With fluorine,
When it's placed into oxygen and nitrogen,
usually fission occurs though when an atom is bombarded with something else to excite it. When it occurs on itself, it is fission still, yes, but usually you just say it's radioactive decay or it's some sort of decay. Fission is traditionally like you have a element that's bombarded with neutrons or something else to cause it to react. All right, when fission occurs, so again, fission traditionally occurs in heavy nuclei. Okay, heavy nuclei. When fission occurs, it releases a lot of energy. Where does the energy come from? Nick.
Breaking apart of atomic bombs, right?
Atomic bonds, very good. So, how is water held together? H2O, right? Hydrogen bonds. If you break those bonds and you can actually harness the energy, a lot of energy comes out of them. It's internal energy that's held in the atom. So when an atom breaks up into different parts, a lot of energy is released due to those breaking of the bonds.
Mr. Hall,
Hmm?
you said that it usually occurs with heavy what?
Heavy atoms. Like traditionally greater than 58 on the periodic table. Number, like proton number, 58. There are a lot of byproducts as a result of fission. One of them are a lot of photons, so you get light. Okay? Protons and neutrons. Photons, protons, and neutrons. When fission occurs, traditional byproducts are photons, protons, and neutrons.
What byproducts?
Photons, protons, and
Yeah, but
neutrons.
what kind of byproducts did you say? Something, you said something before, okay.
You just said byproduct.
We just said byproduct.
All right, let's look at an example of this. Let's look at an example, and then we'll look at a diagram for it. So let's say we have uranium, okay? So uranium-235. Now, this element is so large that even though it has more neutrons than protons, it's still an unstable isotope. Bless you. Okay? So that idea that we want more neutrons than protons helps us with stability, but this is such a large atom that those protons are so far apart that it is considered unstable. Now, if you were to bombard this with a neutron, like a single neutron, what is a neutron, first of all? How would I write that? Does a neutron have any atomic number? It's not one. Nick?
It's all just one AMU.
It's one AMU atomic mass unit, good, but no atomic number, right? So I would write a neutron like this. Okay? What does the one on top stand for?
Mass.
Mass. And it's a neutron. And there's no protons, so the mass has got to be 1, right? Well, 1 neutron. Little n represents neutron, and there's a 1 there, the mass is 1. There's no atomic number here. Okay, no atomic number. Now, when this happens, we get a reaction. Oops.
Wait, Mr. Hall, was that a zero? Yeah.
That is a 0, yes. I just drew a line randomly. Okay, we get a reaction. And the result of this reaction breaks up into 2 smaller nuclei and then some more byproducts. Breaks up into barium, and it's barium 56-140, and krypton. That's krypton 3693. Now, if you were to add your numbers together, you would see that there's not a mass balance. On the left, add the mass together. You get 236. On the right, you get 233. Okay, so we're missing 3 units of mass. So what might the byproduct be? It could be 3 hydrogen atoms, because that's 3 mass, right? Hydrogen atoms, mass of 1. What else could it be? Like 3 protons, pretty much. It could be 3 protons or 3 neutrons. Electrons, remember, the mass is negligible. So the byproduct that can come out of this could either be 3 protons or 3 neutrons. In this case, with uranium, it's 3 neutrons.
Yeah, it doesn't have to be for this one, but it's 56 plus 36 is 92.
Absolutely. Look at your atomic numbers along the bottom. Okay? Look at your balance here. You're going to see this is 92. So had this been 3 protons, it would have been H11, which the top would have checked out for, but the bottom wouldn't have checked out. The 3 is a coefficient. Now, can anybody, and please don't look further in the notes at this point, like focus. Don't look further in the notes, but guess, and feel free to guess, please. If one uranium atom gets hit by 1 neutron, it just breaks apart, right? And as a result, we get more neutrons. So what might continue to happen if I have a uranium core? A cylinder of uranium.
We're like keep occurring, like,
What does that mean? What is that called?
chain reaction.
Yeah, that's exactly right. It's a chain reaction. And let's take a look at what this looks like in a figure. Okay, but this would be a chain diagram. Yes, Scott?
Is that why it's fission, because you can't control it?
No, it's fission because the atomic nucleus is breaking apart. Whether it can be controlled or not has nothing to do with fission versus fusion, but it's fission because uranium breaks up into barium and krypton, and then these 3 neutrons. Okay?
Why does a neutron cause it to break up? Like, wouldn't it make it more stable if you had a neutron?
You know, I don't know. I'm not sure about this one, why it breaks up.
Because like if it's in like matter energy or something, that's cool.
I mean, it's not, yeah, so it's not something that's like, you know, you're just attaching a neutron to it. It's at a high speed velocity. So maybe it's the instability of uranium that just needs like a little kick. You know what I mean?
Yeah.
The idea of a chain reaction though is really important here because this is how nuclear reactors work. Okay, a nuclear reactor will start a reaction and it is a controlled chain reaction, a controlled one. So the idea is that these 3 neutrons hit the next uranium atom in that block or in that core. And those uranium atoms branch off. Making, here it looks like we got a bunch of different things actually. This one broke off into bromine and La.
Lithium.
You're making that up.
No, that's a thing.
Lanthium?
Not, okay, maybe it's not lithium, but it sounds.
Lithium?
No, but that's not lithium.
I know it's not. LA? Anybody know LA?
Lithium.
I've been
It was in a song I heard once.
No, it's lanthanum.
What is it?
Lanthanum.
Lanthanum?
Oh, you get it.
Close. Close. It wasn't exact. Close. So, anyhow, back to the idea. Uranium, okay, breaks into krypton and barium here, but in these other spots, it breaks into rubidium, I know that one, and cesium. Here, lanthanum, and bromine. Okay? Now, the big thing that we want to consider, okay, when looking at chain reactions, is the ability to control a chain reaction. Now, here's some fun facts. And I found this really intriguing. 1 kilogram, what's a kilogram in pounds? Anybody remember?
1,000 what?
What's a kilogram in pounds? It's 1,000 grams. In pounds, anybody remember the conversion?
Like 2 pounds?
It's about 2.2. So a kilogram of uranium, 1 kilogram of uranium. So 2.5 pounds, you can hold in your hand. A 2-pound weight is like this big, okay? That much uranium has the equivalent power or energy that's released by 20,000 tons of dynamite. 20,000 tons. A ton itself is 2,000 pounds. So 20,000 times 2,000 would mean 20 million pounds of dynamite. 20 million pounds of dynamite is equivalent to a handful of uranium in energy released. So think about how much energy comes from nuclear reactions. Okay, it really is catastrophic at times. Again, this was the idea behind the first nuclear bomb, a fission reaction. And today's nuclear reactors are a method of controlled fission, okay, where a system is in place to act in a self-sustaining manner. So fission are the reactors that we see today. We'll talk about why fusion is not soon, okay? But reactors that we have around the country, around the world, nuclear reactors, they're all fission reactors. Okay, fission reactors. All right, now that we've done fission, let's take a look at fusion. It's a nuclear reaction where now instead of splitting, now they
Combine.
combine or come together. Good. Okay? Dragon Ball Z. Anybody? Anybody? Nobody?
Yeah, what about it?
Fusion? Go get it? Remember Vegeta and Goku fused to become Go Get It at one
Wait,
point?
what was that first name?
Okay.
What was that first name?
Vegeta?
What was it?
Vegeta? V-E-G-E-T-A.
Cheetah.
Vegeta. Remember Vegeta and Goku fused? So, hey, where else did you hear fusion? This year, in physics. This year in physics, where else have you heard fusion?
When it's over like that, now we're gonna do it. No one done it.
Think back. Think back.
Oh, you got it.
Come on. 3 people in the other class remember this. Let's go. Work those memories. Where have we talked about fusion before in this class outside of this, on a big scale, with big objects? Where have we talked about fusion?
Like, I think it was energy, like conservation of energy when like they connect and keep going. Like,
Momentum.
Yeah, momentum.
That's it. That's it. Very good. Remember, with inelastic and elastic collisions, the bumpers could fuse together and they move as one mass afterward. So if you forget between fusion and fission, just remember from momentum, when 2 things fuse together, they meant that they stuck together. That's what's happening here. 2 or more nuclei combined. Now, some fun facts about fusion. First, it's lighter nuclei that can combine. So atomic number less than 58. Atomic numbers less than 58. Okay, less than 58. The nucleus again releases an enormous amount of energy. Okay, enormous amount of energy. The byproducts of fusion are different from that of fission. Remember, fission, don't write this, but fission was protons, neutrons, and photons. That was fission. Fusion, its byproducts are gamma rays, positrons, and neutrinos.
Sounds fake.
Okay, positrons and neutrinos. Bobby. Positron, it's spelled like positive, but it's different at the end. And neutrinos. Okay? And then gamma rays, you can spell. Okay, that's the byproduct of fusion. The byproduct of fusion, which is one of the big reasons fusion is so unstable. Byproducts of protons and neutrons and photons and fission, those can be easily controlled. Whereas here, look at the byproducts. You're getting radiation coming off of this. So there's a lot of uncontrolled nature to fusion. And the principle of the first hydrogen bomb was uncontrolled fusion. Okay? Let's look at an example mathematically, or I guess chemically, of what happens. So an example of this. You've got helium 2-3 plus another helium 2-3. Okay? Why are these? These are 2-3 means there's 1 neutron and 2 protons in these atoms. Okay? As a result, we end up getting helium 2-4 okay, and H11 and H11. Ah, dang.
Can you move it up a little?
Yep. I also move because I'm sitting in your way. So, the idea behind this is that you have 2 small nuclei, smaller, I guess relatively speaking, okay? Nucleus with 2 protons and a neutron, 2 protons and a neutron. So there's a neutron, and now there's 4 protons. They fuse together. Out of these 4 protons, 2 of them stay there. Both of the neutrons, there's 1 neutron here and 1 neutron here, both are in here now. And as a result, these are just 2 protons freely floating. Okay, but the nuclei combine to form 1 larger nucleus. A little bit, okay? So fission reactors are things that we currently have. Fusion reactors are theoretical things that we would love to have, okay? The problem with the fusion reactor is that the energy cannot still be controlled. It's the biggest thing. They've tested it out on small scales. They continue to research more and more fusion reactions. But on a large scale, meaning a large scale enough to create energy that we can use, it cannot be harnessed or controlled.
You see the second Batman movie?
I've seen all the Batman movies. I'm trying to think.
Isn't that like the bomb that Baines, like it's not a bomb, it's like a nuclear reactor thingy that Bruce Wayne like made, and then like.
Oh, that was
What is that? Is that this?
the thing that removes all the moisture.
That's the that was Alcock makes though, and like the second spider.
Yeah, that is. Yeah. Because he harnesses like the power of the sun. That's the Spider-Man.
Oh, okay.
But I'm pretty sure because Bane steals the bomb because it's like they did this and then he makes it into like a giant bomb.
It makes it into the nuclear reactor.
Yeah, because I remember the scientist was like a nuclear scientist, the guy that he.
So they made a fusion reactor.
Yeah.
Okay.
I mean, it could have been a fission bomb too.
Yeah.
Because you could make a fission bomb and not control it, but fission reactors are easily controlled compared to fusion reactors. What's an example of fusion? Thank you. A star is a fusion reactor, really. Any star is a fusion reactor. Now, excuse me. Here's another interesting fact. Remember before we talked about dynamite and how much, 1 kilogram of uranium would be? Here's a great one for you. So, fusion's primary fuel source is water, believe it or not. Because fusion generally occurs with hydrogen and helium, smaller atoms. So, if you took, this is wild to think about, 1 gallon of seawater, and you were able to control and harness the energy of fusion from 1 gallon of seawater, it would produce the same amount of energy that's in 300 gallons of gas. Think about that driving for a second. Okay, so you drive, who drives a car? Anybody? All right. How many gallons in your tank, do you know? 24 gallon tank? You have a pretty big, you have a truck?
I have an SUV.
Yeah, 24 gallons makes sense. If you have a small car, 12, 15 gallon tank. All right, let's say we've got a 20 gallon tank and that car gets 20 miles a gallon. That means that every full tank is 400 miles and you have to fill up, which makes sense. It means you can drive from here to like Maryland, and then, further than Maryland actually, 400 miles, a little bit further. Now imagine though, for every gallon of gas that you would put in your car, okay, you would only have to put 1/300th of water in your car. So if you put a gallon of water in your car, it's like you're filling up a 300 gallon tank of gas if you could harness and use that energy. So 1 gallon of water would travel as far as 300 gallons of gas. 300 gallons of gas at 20 miles a gallon travels 6,000 miles. So a gallon of seawater could bring you 6,000 miles away.
And can't they use fusion?
The U.S. is only 2,400 miles across. So 1 gallon of water, you could do almost 3 trips on 1 gallon of seawater if they could harness the fusion power of water.
So, what do you mean if? Why can't
It
they?
hasn't been done yet. It hasn't been
It's
controlled.
harder.
I don't know too much about radiation, but I do know that the reaction that occurs is a very unstable reaction.
How much money would one get if they could figure this out?
A lot.
I'm assuming lots, obviously. I mean,
Water into
there
gas.
are
That's all
cars.
they do.
There are cars like, what are there, hydrogen cars now, right?
Yeah.
That they've started using, and the byproduct is only water vapor, I think.
Yeah, how much do
drips
those
out.
cost? Like,
They're expensive. The technology was, I don't know. Anybody car buff that would know how much cars like that cost?
I'll look it up.
The auto show's coming to New York soon.
It's
It's probably it's already here.
Yeah.
Oh, it passed?
27.
Yeah.
So this weekend.
Yeah, but you could.
Oh, it's been since. Gotcha. So I don't know, Mike, but yeah, it would be a ton of energy they'd be getting out of it. All right, let's pause there for the day. Let's pause there, or that's it for the work is 3 questions. Hey, I really recommend you watch this. I don't usually put video assignments. It's really does a great job of explaining fusion and fission. Okay, only watch the first 7.5 minutes. After that, you can keep watching if you want, but it's not really stuff we did in class.
Do you know the name of